Continuing on with the Chem 112 Organic Chemistry 1 lecture series, we're going to be focusing now on Chapter 10, which discusses mass spectrometry and infrared spectroscopy. This is the first in a series of chapters focusing on characterizing molecules. And what that means is we're going to be able to collect data on a given sample, and from that, we can determine the formula and structure of a molecule using this collected spectroscopic data. Now, before we talk about infrared spectroscopy and mass spectrometry, we're going to talk about a fundamental method to determine the molecular formula, which is elemental analysis. So the mass percentage of each element in a sample can be determined via elemental analysis. In elemental analysis, a sample is decomposed, and then the products are collected, which in turn, by measuring the mass of these decomposition products, we can in turn determine the mass percentage of each element found in our sample. There are a range of elemental analysis methods that each function a little bit differently, but the end output of elemental analysis remains the same. You have as an output from elemental analysis the mass percentage of each element found in your sample. This allows the empirical formula to be calculated, and we've done these sorts of calculations a lot in general chemistry. So let's do an example. Suppose you have a sample and you determine via elemental analysis that it's 88.16% carbon and 11.84% hydrogen by mass. From these mass percentages, we can calculate the moles of each element by taking the mass divided by the molar mass of each element. This gives us the moles of carbon and hydrogen, and we can determine the empirical formula by taking the mole-to-mole ratio. Looking at the mole-to-mole ratio of hydrogen to carbon, we get a mole-to-mole ratio of 1.6 moles of hydrogen per 1 mole of carbon. Now, in order to convert this decimal into a whole number, we're going to multiply this decimal ratio by a whole number. Why did we choose 5? Because 0.6 times 5 gives us a whole number 3. You can also think of the fact that 1.6 corresponds to the fraction 8 over 5. So we're going to multiply this fractional ratio by the whole number ratio 5 over 5, and this gives us a ratio of 8 moles of hydrogen per 5 moles of carbon. This gives us an estimated formula, empirical formula of C5H8. So as we can see, because elemental analysis gives us the mass percentage of each element, we can use those mass percentages to calculate the empirical formula for a given compound. Elemental analysis is really useful because we run reactions that could generate impurities, or as a result of using reagents that have metal ions and other species that are difficult to detect, elemental analysis can be used to help detect metal impurities and other impurities found in our sample that would be IR and NMR silent, or at least difficult to detect via common spectroscopic methods. So elemental analysis allows us to verify the identity, the purity, and the composition of our compound. Now, once we have a formula, we can use this idea of degree of unsaturation to estimate the structural features and functional groups found in a compound with that formula. As a refresher, unsaturated compounds are compounds containing pi bonds or rings. The degree of unsaturation is the number of multiple bonds or rings found in your compound. Du can be calculated using the provided formulas. Let's put these formulas into practice and let's calculate the du for the following formulas. For C6H6, the du would be 2 times the number of carbons, which is 6, plus 2 minus the number of hydrogens divided by 2. This gives us 14 minus 6 over 2, which is 8 over 2, which is a du value of 4. That makes sense. This formula matches that of benzene, which has a du of 4. 3 pi bonds plus a ring gives us a total du value of 4. Let's now try to apply what we've learned, and I'd like you to work on these next two examples, and I'd like you to calculate the du for the following two formulas. So pause the video, work through these examples, and then we'll discuss. Okay, so in this case, C3H5NO2, this is a nitro group. So I'm expecting a du value of at least 1. You'll see in a moment why that is. So calculating our full du value, we have 3 times 2 plus 2. So 2 times the number of carbons plus 2, plus 1 for the number of nitrogens, minus 5 for the number of hydrogens, divided by 2. This gives us a du value of 6, 7, 8, 9 minus 5 over 2, 4 over 2, which is a du value of 2. This gives us a potential formula that looks like this. And the reason why I said we would expect a du value of at least 1 is this nitro group has a pi bond. The NO2 group, which matches the nitro group, contains a nitrogen-oxygen pi bond, so you'd expect a du value of at least 1. This compound has a du value of 2 because it has 1, 2 pi bonds. Looking at this last formula, CH3CN, that is a common solvent. That's just acetonitrile, which has a du value of 2. Let's prove that now by taking 2 times the number of carbons, plus 2 plus the number of nitrogens, minus 3 for the number of hydrogens divided by 2. This gives us a du value of 7 minus 3 over 2, which is 4 over 2, which is a du value of 2, which makes sense because our structure has 1, 2 pi bonds. Let's now shift gears, and instead of calculating du from a formula, let's calculate du given the structure. In this case, you just count the pi bonds and rings. For example, in this molecule, we have 1, 2, 3, 4 pi bonds plus a ring, giving us a du value of 5. I'd like you to try to calculate the du for these next two structures. So pause the video, take a few moments, and then we'll discuss. Okay, so in this molecule, we have 1, 2 pi bonds and a ring, giving us a du value of 3. In this next case, we have 1, 2, 3 pi bonds, so we have a calculated du value of 3. Okay, so we've gotten pretty proficient at calculating the formula from data collected from elemental analysis, such as the mass percentage, and we've seen how we can use the formula to calculate du and estimate the number of pi bonds and rings found in a structure matching that formula. Let's talk next about one of our first methods to characterize compounds, which is mass spectrometry. So in mass spectrometry, a sample is ionized and the resulting ions and fragments are analyzed. This ionization occurs via what's known as electron impact, where a sample is vaporized and bombarded by high-energy electrons that removes a valence electron. This makes what is known as a radical cation. And unfortunately, this radical cation can then undergo fragmentation to generate fragment ions. So whenever you ionize a compound via electron impact, you get a radical cation, but you also get a fair amount of fragmentation and rearrangement. Mass spectrometry is pretty useful in that it measures the molecular weight by measuring the charge to mass ratio. The way that we can measure the mass to charge ratio and the way that we can separate all of these ions that we're generating is using a magnetic field. As compounds pass through, specifically as the ions pass through the magnetic field, the ions will deflect based on their mass to charge. This allows us to separate ions based on their mass to charge, and in turn, we can measure the abundance or relative amount of each ion generated as a result of ionization and the fragmentation of our ions. Now, what does the output look like? What does the mass spectra look like? Well, the mass spectra is a plot of the mass to charge of our ions. So our mass over charge is on the x-axis versus the intensity of the signal, which roughly corresponds to the number of ions on the y-axis. We call the relative amount of each ion the relative abundance. There are two additional features that you want to pay attention to and two terms that we use to describe peaks in the mass spectra. The tallest peak is known as the base peak. So for example, this tallest peak will be the base peak. More importantly, the peak that corresponds to the unfragmented radical cation is known as the parent peak or the molecular ion. For example, propane with a molar mass of 44 has a parent ion peak with a mass over charge of 44. The parent ion or the molecular ion is denoted by the notation M radical plus, denoting the fact that this parent ion is a radical cation. So how can we interpret the mass spectrum? Well, let's talk about the first main thing that we can do. The mass spectrum provides the parent peak molecular ion mass with a high precision. If you're using high precision mass spectrometry, you can differentiate compounds solely using the high precision molecular ion mass. For example, we can differentiate C5H12 and C4H8O based on the small difference in molecular mass. So from the molecular ion mass, we can precisely determine the molar mass of our compound, and in turn, precisely determine the formula if you calculate the molar mass using the precise atomic masses. In practice, many instruments have a set of databases that they can use where it will interpret the mass and in turn provide you with an estimated formula. You may say, why don't we just stop here? The instrument can do all of the work. In practice, it's good to know how to interpret other parts of the mass spectra, and you may not always be working with a mass spectra that's sufficiently high precision. So, we're now going to discuss how to interpret each part of the mass spectra and how we can use the mass spectra to describe and differentiate compounds based on their fragmentation patterns and based on their spectral features. So the first thing that we're going to look at is the molecular ion peak. The mass of the molecular ion peak can help to determine the degree of unsaturation. If there's a pi bond or ring, the parent ion peak will have a mass that's 2 less compared to the saturated molecule. For example, pentane versus 1-pentene. 1-pentene has a DU value of 2, and so we lose 2 AMU in mass because we've lost 2 hydrogens. Sorry, this should be a DU value of 1, and the mass is 2 AMU less. So as you can see, for each pi bond or ring that we add, our mass decreases by 2 because we've lost 2 hydrogens. Another rule to keep in mind is the nitrogen rule, where an odd molecular weight implies an odd number of nitrogen atoms. So for example, if we have an odd number of nitrogen atoms, our molar mass or molecular weight will be an odd number. This nitrogen rule is really helpful to keep in mind, as if we can determine the presence of nitrogen in our structure, we can look out for some other features that can help us confirm the presence of nitrogen. So if you look at the molecular ion peak, pay special attention to the mass. You can use it to estimate the degree of unsaturation, and you can also use the fact that if your mass is odd, you have an odd number of nitrogen atoms. Now, there is a special case to note where you may not always see your parent ion or the molecular ion. In some cases, the parent ion may fragment heavily, requiring soft ionization or alternative ionization methods. For example, 2,2-dimethylpropane readily fragments to generate a very stable fragment ion. As a result, you will not see the parent ion. This can happen. It's something to look out for. So it's really important to make sure that the ion that you're paying attention to is actually the parent molecular ion. This happens in a few cases, but I wanted you to be aware of it. Okay, let's now talk about interpreting different parts of the mass spectra. The first part that we're going to look for is the M+1 peak. So there are going to be small peaks above the molecular weight that are found adjacent to the molecular ion. These appear due to naturally occurring heavier isotopes found in the sample. Now, specifically, the M+1 peak primarily arises as a result of carbon-13 that is randomly present in your sample. Because carbon-13 is roughly 1.1% of all carbon atoms in nature, for each carbon in your molecule, the M+1 peak increases in height by 1.1% of the parent peak. You can think of it as the M+1 peak increases by 1.1% per carbon atom found in the formula. To show you an example of what this looks like, taking a look at the structure of decane, decane has a formula of C10H22. As we can see, here is the M+1 peak, and the M+1 peak is 11% the height of the base peak or the parent ion peak. Where did we get this 11% from? If we have 1.1% of the M+1 peak height per carbon, multiplying by 10, this gives us 11%. So as you can see, the more carbons that we have, the larger the M+1 peak becomes. And we can use the M+1 peak height to calculate and estimate the number of carbons found in our sample. To really highlight and showcase this point, for isoocane, which has a formula of C20H42, the M+1 peak is 22% the height of the parent ion peak. The reason why this M+1 peak is larger is because we have more carbons. Where did this 22 come from? If we have 1.1% peak height per carbon and we have 20 carbons, that gives us an M+1 peak height of 22%. So we can use the M+1 peak height to estimate and calculate the number of carbons in our formula. Further, if you have a hydrocarbon, the number of hydrogen atoms can be calculated by taking the molecular ion mass minus 12 times the number of carbon atoms. Let's show an example of this kind of calculation. So in this case, we're asked to provide a reasonable formula for the following mass spectra data. We are given that we have a molecular ion mass of 54, and the relative height of our peaks is that the M+1 peak has a relative height of 4.6. So if we wanted to calculate the number of carbons, we take the relative height of the M+1 peak divided by 1.1%. This gives us 4 carbons as our estimated carbon count. If we wanted to figure out the mass of hydrogen, we take our molecular mass minus the number of carbons times the molar mass of carbon, which is 12. That gives us 6 hydrogens. And given that hydrogen has a mass of 1 gram, if we calculate that we have 6 grams of hydrogen, and hydrogen has a mass of 1 gram per mole, we would expect that we would have 6 hydrogen atoms in our formula. This gives us a calculated formula of C4H6. So as you can see, for hydrocarbons, we can use the parent ion mass along with the relative height of the M+1 peak to calculate the number of carbons, and in turn calculate an estimated formula for our compound. Let's now turn our attention to another very important peak. Let's talk now about the M+2 peak. Now, you will not always see an M+2 peak, but the M+2 peak is very important if it's present because it's a signpost that you have a halogen in your compound. Specifically, let's talk about the M+2 peak for chlorine-containing compounds. So chlorine consists of chlorine 35 and 37, with chlorine 35 being the major isotope at 75% abundance. Compounds with a chlorine atom will have an M+2 peak roughly 25% the height of the parent ion peak. Chlorine is also evidenced by loss of exactly 35.5 mass over charge, loss of a chlorine atom, and loss of the M+2 peak during fragmentation. So there are 2 pieces of evidence that suggest you have chlorine present in your compound. The first of which is this M+2 peak that is 25% of the parent ion peak. So if you observe an M+2 peak that's 25% the height of your parent ion, that's one signpost that you have a chlorine atom. The second signpost is that during fragmentation, you will often lose chlorine, and this is indicated by a loss of mass of about 35 mass over charge. So for example, in this case, we start with a mass over charge of about 112, and after loss of chlorine, we end up with a mass over charge corresponding to 77. This difference indicates a loss of 35 AMUs of mass, which corresponds to the loss of chlorine. So we can use and check for the M+2 peak. The relative height of the M+2 peak tells us that we have chlorine if the relative height is 25%. And you will also see fragmentation corresponding to the loss of chlorine, the loss of 35 AMUs during fragmentation. Let's talk about another possible M+2 peak, which comes from bromine. So bromine in comparison to chlorine, consists of bromine 79 and 81, with both isotopes having 50% natural abundance. Compounds with a bromine atom will have an M+2 peak with an equal height compared to the parent ion peak. Bromine is also evidenced by the loss of exactly 79.9 AMU and loss of the M+2 peak during fragmentation. So if we go and take a look at a spectra for a compound containing bromine, in this case, as you can see, we have an M+2 peak of equal height to our parent ion peak. This is a key signpost that bromine is present in your sample. Additionally, as you can see, during fragmentation, the loss of bromine corresponds to fragmentation with the loss of 79.9 AMUs. So we go from a mass of, in this case, we have two fragments, one at 108 and the other at 110. And after fragmentation and loss of bromine, we end up with a fragment with a mass over charge of 29. This difference in mass corresponds to the loss of bromine, the loss of 79.9 AMUs of mass. So you can look both at the M+2 peak and the fragmentation pattern to determine whether bromine or chlorine is present. Let's talk about other fragmentation patterns. This time, let's talk about the common fragmentation patterns of different compounds. So hydrocarbons will fragment by breaking carbon-carbon bonds, and the largest peak is going to be the most stable cation. Generally, hydrocarbons will fragment to yield fragments containing the most stable carbocation. For example, in this case, fragmentation occurs breaking the following carbon-carbon bond because it yields a very stable tertiary carbocation. Generally, the more stable fragments will have the largest abundance values. They'll appear as larger peaks in the mass spectra. When we talk about functional group specific fragmentation, it's important to talk a little bit about the fragmentation pattern of alcohols. Alcohols undergo what's known as alpha cleavage, where they break the carbon-carbon bond and lose the group adjacent or alpha to the alcohol. So when this alcohol undergoes alpha cleavage, you generate a stabilized cation because your cation's adjacent to this pi donor. Alcohols can also dehydrate, losing water, losing 18 mass over charge units, or losing 18 AMUs of mass to give a carbon-carbon bond. So let's take a look at an actual spectra of an alcohol. In this case, we're looking at 2-pentanol. And let's look at the different fragments generated during fragmentation, and let's see how we can explain this fragmentation pattern using what we've learned. So in this case, 2-pentanol, the parent ion would have an expected mass over charge of 88. Notice we don't really see the parent ion. 2-pentanol fragments readily, and we primarily see the fragments. One fragment occurs via alpha cleavage that I'll call alpha 1. In this case, fragmentation yields the following two ions, the first of which has a formula of C2H12345O. This gives us a mass over charge predicted of 24 plus 16 plus 5, or 45. This propyl cation fragment has a formula of C3H7. and that has a mass to charge of 36 plus 7, or 45. So both of these fragments have a mass over charge of 45, and that explains why this peak is so large in the mass spectra. You can also see alternative fragmentation at the other alpha position to generate this fragment with a formula of 1, 2, 3, 4, C4H 1, 2, 3, 4, 5, 6, 7, 8, 9, which has a mass over charge value of 48 plus 9 plus 16, which is 57 plus 16, which is 73. So this fragment here corresponds to alpha cleavage at the other alpha position. Why do we see more alpha cleavage at position that I labeled alpha 1? Well, you get a slightly more stable carbocation. Primary is a little bit more stable than a methyl carbocation. Now, as you can see, we've used the fragmentation patterns that we've discussed to explain and identify each of the major fragment ions in this mass spectra. It's really important to be able to think about how can I generate this fragment ion, because you can draw and estimate the structure of these fragment ions, and you can start to put those fragment ions together to estimate the structure of your parent compound. So we concluded our discussion of the alcohol fragmentation patterns. Let's talk about the fragmentation patterns for amines now. So amines also undergo alpha cleavage, where you break a carbon-carbon bond and lose the group alpha to the amine. Again, the driving factor is you generate a stabilized carbocation. Amines can also generate M-1 peaks, and these are very characteristic of amines, and these can be observed for amines via the loss of hydrogen. So let's see these fragmentation patterns in practice. So here, we have the spectra, the mass spectra for triethylamine. So here is triethylamine. We have the structure shown in the upper right-hand corner. Our molecular ion mass over charge is calculated to be 101. So we see that right here. We have our parent ion. I would also like to draw your attention to a minor peak adjacent, which corresponds to the M-1 peak with a mass over charge value of 100. Here is the M-1 fragment, which is formed via loss of a hydrogen atom. In addition to this M-1 peak, we also observe alpha cleavage, where we have loss of a methyl group via alpha cleavage to generate this alpha cleavage product with a mass over charge of 86. One way that we could tell that we've lost a methyl group is that this difference in mass is equal to 15, which corresponds to a methyl group fragment. So, as you can see from this spectra for triethylamine, we were able to observe and identify the two major fragmentation patterns for amines: alpha cleavage and loss of hydrogen to generate an M-1 peak. One way we can further demonstrate a nitrogen is present is if we take a look at this mass, we see that we have an odd mass for our overall compound mass, which indicates we have an odd number of nitrogen atoms. So an odd molecular mass is a signpost that you should look for that indicates that nitrogen is most likely present. The M-1 peak provides another piece of evidence suggesting that nitrogen is most definitely present in this compound. Now, when we talk about aryl and benzyl groups, they have some pretty common fragmentation patterns in that aryl groups will commonly fragment to yield the C6H5 fragment with a mass over charge value of 77. This is a pretty stable fragment. Benzyl compounds are pretty interesting in that they will often fragment to yield the C7H7 fragment. Although you may think this fragment exists as a benzylic cation, it actually rearranges to exist as what's known as the tropylium cation, which is a very stable aromatic cation with a mass over charge of 91. So whenever you're dealing with aryl and benzyl compounds, just be on the lookout for these fragments as they will almost undoubtedly be present in the mass spectra. Okay, let's talk a little bit about some common fragmentation patterns for carbonyls. So for carbonyls, using notation, we can label the position adjacent to the carbonyl as alpha, 2 carbons away as beta, and 3 carbons away as gamma. This rearrangement resembles, if you've been reading ahead, a textbook 3-3 rearrangement. In this case, the carbon-hydrogen bond that is 3 atoms away on the gamma carbon participates in an internal transfer of a proton to the carbonyl group. This is called the McLafferty rearrangement, and as a net result, we end up forming an oxygen-hydrogen bond, forming a carbon-carbon bond, and breaking a carbon-carbon bond between the alpha and beta positions. This McLafferty rearrangement generates an alkene and an enol-like species. Now, in addition to the McLafferty rearrangement, carbonyl compounds can also undergo alpha cleavage, where you break the carbon-carbon bond adjacent to the carbonyl, and in turn, again, the driving factor behind this is you can generate a stabilized cation. So let's see these ketone fragmentation patterns in practice. So here is a literature spectra of the following aryl ketone, and let's take a look at its fragmentation pattern. All of these spectra are obtained from laboratory spectra databases, and I really think it's important to look at actual experimental spectra because they contain a lot of information, and getting used to interpreting these kinds of experimental spectra is very useful because the spectra that you see as part of these lectures are going to be very similar to the spectra you encounter as part of your laboratory practice. So first and foremost, this compound has a mass, and we would expect the molecular ion mass to be about 148. We see our molecular ion peak right here. In addition, we have some alpha cleavage fragmentation patterns. So in this case, we can undergo alpha cleavage at position 1. This would generate the following fragment with a mass over charge of 105. We can also observe alpha cleavage at the other alpha position. This generates the following aryl radical cation with a mass over charge of 77. Now, in terms of where this fragment with a mass over charge of 120 comes about, this comes about via a McLafferty rearrangement. To show how that occurs, I'm going to draw this molecule. Okay, here we go. From here now, we can initiate the textbook McLafferty rearrangement, where we form the oxygen-hydrogen bond, we form a carbon-carbon double bond, and we break a carbon-carbon single bond. As a net result, we end up with the following enol-like fragment, which has an observed mass over charge value of 120. So this fragment is a result of the McLafferty rearrangement. So as you can see, we were able to observe the major fragmentation patterns for ketones in the following spectra. Let's now talk a little bit about how we can use the mass spectra to calculate the formula for a compound. I want to be clear that the mass spectra is used in combination with other spectroscopic methods. With that said, the molecular formula and structural features found in your compound can be elucidated with mass spectroscopy. The first thing that you're going to do is you're going to find the parent ion and you're going to find the molecular ion mass to charge value. From the molecular weight, the formula can usually be determined if you're collecting a high resolution spectra. If not, what you're next going to do is you're going to check for the M+1 peaks. The M+1 peak percent height can be used to estimate the carbon count, given the M+1 peak increases in height by 1.1% based on the number of carbons in your formula. Next, you're going to check for M+2 peaks. If the M+2 peak is 25% of the parent ion peak, you have chlorine. If the height is equal, if the M+2 peak is equal in height, you have bromine. Finally, you're going to check for M-1 peaks. Those are a signpost you have nitrogen. If the molecular mass is odd, then nitrogen is most definitely present. So let's take a look at an example and let's show how we can calculate the formula from the mass spectra. So I want to be clear that the abundances and the relative peak heights of the M+1 and M+2 peaks can be read from the spectra, but you can also determine the relative peak height of the M+1 peak using the abundance values. So in addition to the spectra, the mass spectrometry instrument will give an output, a abundance chart, where you're given the mass over charge of each ion along with the relative abundance. You can use the relative abundance values to calculate the percent height of each peak. For example, looking at the following compound, here is the spectra, in this case for hexane. We have our parent ion, our molecular ion peak, and all the way down here is the M+1 peak. It would be hard to get an accurate percent abundance estimation visually, so we use our abundance table. As you can see, we can see our M+1 peak, and to figure out the number of carbons in the formula, what we're going to do is calculate the percent height of the M+1 peak by taking the abundance of the M+1 peak over the abundance of the parent ion peak. This gives us a percent height of 6.6%, and to calculate the number of carbons, we take this 6.6%, divide it by 1.1, and this gives us an estimated value of 6 carbons. In this case, we know that for the mass of carbon, we have 6 carbons, and carbon has a mass of 12 AMU. So this gives us a mass of 72 AMUs of carbon atoms. To figure out the mass of hydrogen, we take our total mass minus the mass of carbon, and the remainder of 12 AMU indicates the mass of hydrogen. From here, we can calculate the number of hydrogens by taking the mass over hydrogen's atomic mass, which is 1. This gives us an estimated number of hydrogens of 12 and a formula of C6H12. In this case, we have a DU value calculated of 6 times 2 plus 2 minus 12 over 2, which gives us a DU value of 1. That tells us that we aren't quite looking at hexane, but instead, this is likely a hexene compound. So, as you can see, we can use the abundance of the M+1 peak along with the parent ion mass to calculate the number of carbons and hydrogens and thus estimate the formula for our compound. Let's now talk a little bit about interpreting the mass spectra from the perspective of fragmentation. So fragmentation can be used to differentiate compounds. Some common fragments include the methyl ion fragment, the ethyl ion fragment, the aryl radical cation fragment, and the tropylium ion fragment. In terms of how we go about interpreting fragmentation, I prefer to take what's known as the retrosynthetic approach, where you start by identifying your parent ion mass to charge. What you're then going to do is you're going to look for fragments close to the parent ion and draw the structure of those fragments. From there, you're going to combine fragments and draw the new structure, and you're going to repeat this process until the parent ion mass is obtained. Essentially, you're drawing out plausible structures for each fragment, and then you're combining the fragments until you get to your parent ion mass. And by putting the fragments together, you're slowly piecing together your full structure. Now, in practice, mass spectrometry is often used to differentiate two similar compounds based on fragmentation. For example, let's take a look at how we can differentiate ethyl cyclohexane and 1,1-dimethylcyclohexane. So in this case, both of these compounds have a DU of 1 and they have the same formula of C8H16. Here is ethyl cyclohexane, and let's take a look at the other compound, which is 1,1-dimethylcyclohexane. Now, these compounds cannot be differentiated using the parent ion mass. They have the exact same mass, exact same formula. They can be differentiated via fragmentation. So because compounds will generally fragment to generate the most stable ions, for ethyl cyclohexane, we'd likely see fragmentation where we lose this ethyl group and generate this stabilized cyclohexyl cation. Now, this ethyl group and the ethyl cation, we'd expect to have a mass to charge of 29, while this cyclohexyl cation has a formula of C6H5, which has a mass over charge of 6 times 12 plus 5, which in turn, oh, sorry, this wouldn't be C6H5, it's H 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it would be 6 times 12 plus 11, which in turn gives us 72 plus 11, which is 83. So we have an expected mass to charge value of 83. Looking at the fragmentation of 1,1-dimethylcyclohexane, we'd expect to lose a methyl group during fragmentation and generate this methyl cyclohexyl cation with a mass over charge value of 98 and a formula of C7H1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We'd also get a methyl fragment, but that methyl fragment is going to be very hard to detect. So let's take a look at the spectra now. And as you can see, both spectra, or in this first spectra, we see our parent ion with a mass over charge value of 112. We also see in the first spectra that we have a major ion with a mass over charge of 83. This matches the fragmentation pattern for ethyl cyclohexane and matches the mass over charge value for this cyclohexyl cation. So I'm going to assign this first spectra as matching ethyl cyclohexane. By the same token, looking at this second spectra, we see that this parent ion peak is very small. And this suggests that fragmentation occurs readily to generate this fragment ion with a mass over charge value of 98. This directly matches this cyclohexyl cation that we assigned as part of the fragmentation pattern of 1,1-dimethyl cyclohexane. Thus, I'm going to assign this second spectra as matching 1,1-dimethyl cyclohexane. As we can see, we can differentiate these two compounds based on their fragmentation patterns and their expected fragment ions. So this is a really important way that you can use mass spectrometry to differentiate compounds. So the way to approach these problems is to draw out the structure of the two compounds, draw out the expected fragmentation, so start breaking carbon-carbon bonds to give stable cations, calculate the mass over charge value for those cations, and see if those peaks are present in any of the spectra. In many cases, the two compounds, even though they have the same formula, will have differences in structure that yield differences in their fragmentation patterns. And we can use their different fragmentation patterns and those different fragment ions to differentiate our two compounds. Okay, let's do some practice now. And for the first part of this practice problem, I'd like you to, given the following spectra and peak data, I'd like you to propose a formula for this compound. So again, we have a spectra along with the peak abundance for the parent ion and the M+1 peak. So take a few moments and calculate the formula for this compound, and then we'll discuss this problem momentarily. Okay, so first and foremost, we know our parent ion mass is 84. In order to calculate the percentage of our M+1 peak, we're going to take the abundance of the M+1 peak over the abundance of the parent ion peak times 100%. If you punch this into your calculator, you'll end up with a percent abundance of 6.6%. To calculate the number of carbons, we take 6.6 over 1.1, and that gives us an estimated carbon count of 6. Now, to calculate the mass of hydrogen, we take our overall mass minus 6 times the atomic mass of carbon, which is 12. This gives us a mass of hydrogen of 84 minus 72, which is 12, which gives us a number of hydrogen atoms of 12. This gives us a formula of C6H12, and we calculated du in this case of 2 times 6 plus 2 minus 12 over 2, which gives us a du value of 1. So we can use the percent height of the M+1 peak to estimate the number of carbons and in turn estimate the number of hydrogens. So let's look at the next part of this problem. Here, below is a second spectra. These two spectra are either 2-hexene or 2-methyl-2-pentene, and you have to assign the identity of each spectra. So take a moment and look over these two spectra. And I'd like you to tell me which of these two spectra corresponds to 2-hexene and which of these two spectra correspond to 2-methyl-2-pentene. And to give you a hint on this, let's draw out the structure of our two compounds. So 2-hexene looks like this, while 2-methyl-2-pentene looks like this. They each have the same formula of C6H12 and a expected parent ion mass over charge value of 84. So in this case, you're going to have to differentiate these two compounds based on their fragmentation patterns. So take a few moments, take a look at each of these two spectra, and I'd like you to tell me which spectra corresponds to which compound. So pause the video, take a fair amount of time to look through these spectra and calculate the fragmentation patterns, and then we'll discuss. Okay, so first things first, let's look at expected fragmentation patterns. For 2-hexene, it's going to fragment to yield the most stable cation, which I would expect to be an allylic cation. Now, given that we have this allylic cation, it has a formula of C4H123456, which corresponds to a mass over charge value of 12 times 4 plus 7, which corresponds to a mass over charge value of 55. The ethyl group has a mass over charge of 29. By comparison, 2-methyl-2-pentene would fragment via loss of a methyl group, giving the following cation, which has a formula of C5H12345678, which corresponds to a mass over charge value of 69. As we can see in this second spectra, we see a very, very large peak corresponding to a mass over charge value of 69, which directly maps onto this expected fragment. I'm going to tentatively assign this spectra then as 2-methyl-2-pentene based on this fragmentation pattern. Let's take a look at our other spectra up top. Here we see we have our parent ion, and we see a large peak with a mass over charge value of 55. This directly matches the expected fragment cation. Further, we also see this ethyl fragment that appears much larger in this spectra. So I'm going to tentatively assign this top spectra as corresponding to 2-hexene. As you can see, these two compounds have dramatically different fragmentation patterns because based on their structure, they fragment to yield dramatically different major fragment ions. So we can use the predicted fragmentation patterns to differentiate compounds because different structures will fragment slightly differently. Wonderful. So we've gone through a full example where we calculated the formula and estimated the structure for a compound based on its fragmentation pattern as observed in the mass spectra. Let's now do some additional practice, and let's practice interpreting the mass spectra. And I'd like you to tell me, in these two given spectra, if nitrogen, chlorine, or bromine is present in each of the following samples based on their spectra. So pause the video, be very careful observing these two spectra, and then we'll discuss. Okay, so nitrogen, chlorine, and bromine. For nitrogen, we're looking for an M-1 peak. Chlorine and bromine, we're looking for an M+2 peak. So looking at this first compound, the molecular ion mass to charge is 45. I don't see much of anything in the M+1 region. So if here's our M peak, right here next to it is an M-1 peak. This tells me that nitrogen is present. What's another hint? This mass to charge is odd. So I have two pieces of evidence, the odd mass as well as the presence of an M-1 peak that tells me nitrogen is present. Let's look at this next case. So here we have our molecular ion mass over charge is 78. So here's our M peak. We see we also have an M+2 peak, and this M+2 peak is about 25% of the height. This tells me that chlorine is present. Let's do a secondary check to verify this. So if we have a mass of 78 and we lose chlorine, 78 minus 35 gives us 44. And we see this huge peak at mass over charge of 44. So this gives us another piece of evidence that chlorine is present. So it's not just the height of the M+2 peak, but also the fact that if you lose chlorine, you will lose the mass of chlorine during fragmentation. Wonderful. Okay, so let's now do a slightly advanced example, but one that simplifies dramatically if you identify the two fragment ions. So for this spectra, I'd like you to provide a formula for this compound. And I will tell you that the molecular ion mass to charge value is 108. Now, take a few moments to work through this example, and then we'll discuss. Okay, this example looks a lot harder than it is. First and foremost, I see I have my mass peak and I have an M+2 peak of equal height. What this tells me immediately is that bromine is present. So I have bromine present. Additionally, fragmentation with loss of bromine gives me a fragment with mass over charge of 29. This is an ethyl cation fragment. So putting these two fragments together gives me ethyl bromide, which has the calculated mass value of 108. So this compound's structure is ethyl bromide, and its formula would be C2H5Br. So as you can see, if you pay attention to the fragmentation patterns, pay attention to the M+1 and M+2 peaks, you can in turn very easily assign the structure of a compound. Let's do another practice problem. In this case, this involves interpreting fragmentation patterns, this time for alcohols. So below are the spectra for 1-propanol and 2-propanol. I'd like you to assign the identity of each spectra and draw reasonable structures for each major fragment peak. So just for reference, 1-propanol looks like this, while 2-propanol looks like this. So I'd like you to take a few moments, carefully observe each of these spectra, and then I'd like you to assign the identity of each spectra by matching each spectra to each compound, and I'd like you to draw the structure of the major fragment ions. So pause the video, work through this example, and then we'll discuss. So in each case, let's start by looking at the first spectra. So here we have a mass to charge value. So looking at its formula, we have a formula of C3H123456780, which gives us 36 plus 8 plus 16. Okay, that gives us 44 plus 16, which gives us 60. We're not seeing much of our parent ion. In fact, we see this mass to charge of 59. Okay. We also see a large peak with a mass over charge of 45. This signifies a loss of mass of 15. So we may be losing a methyl group. Now, let's take a look and let's do some predicted fragmentation. So alpha cleavage in compound A, you'd expect to get the ethyl cation with a mass over charge of 29, and the following cation with a formula of CH3O, or 15 plus 16, 31 as the mass over charge. By comparison, alpha fragmentation in 2-propanol would yield the following cation plus a methyl cation. The methyl cation has a mass over charge of 15, while this cation has a mass over charge value of 45. C2H5O, or 24 plus 5 plus 16, gives us a mass over charge of 45. So it appears to me like this large fragment here matches the following cation fragment, and this suggests to me that this first spectra corresponds to 2-propanol. By comparison, looking at the second spectra, we see our parent ion, and we see a large peak with a mass over charge value of 31, which directly matches our predictions for the following fragment. So this suggests to me that this second spectra corresponds to 1-propanol. So as you can see, we've used the fragmentation patterns for alcohols to differentiate these two alcohols, and we've gone a step further and we've assigned and drawn out the perspective structure of each of the major fragment ions. So as you can see, mass spectrometry can be used to differentiate two compounds based on their fragmentation patterns. This concludes our discussion of mass spectrometry. The second part in this Chapter 10 lecture series will then move on and adjust our discussion to begin a discussion of infrared spectroscopy. So we're going to conclude this first part of the lecture series, and we'll continue on and discuss infrared spectroscopy in the next lecture video.